In this lecture, we will discuss about the basic concept regarding the orbital angular momentum in quantum mechanics, and the content of the lecture is from the textbook of M.C. Jain. Now, what is orbital angular momentum? But before the discussion, it should be mentioned that in the previous lectures we have shown the application of quantum mechanics to some systems with one dimension. But apart from the one dimension, there are several applications of quantum mechanics to some three-dimensional systems also. And an important new concept that appears is that of angular momentum. So, to describe the application of quantum mechanics in three-dimensional system, one important topic, that is angular momentum, need to be discussed. In classical mechanics, the angular momentum is one of the three fundamental constants of motion of an isolated system. We all read about this concept. So, angular momentum is one of the three fundamental constants of motion, the other two being energy and linear momentum. In classical mechanics, we have read about conservation of energy, conservation of linear momentum, and conservation of angular momentum. It turns out that this statement is also true for isolated quantum mechanical systems. So, this is also true for isolated quantum mechanical systems. The correspondence principle also demands that this must be so. The conservation of angular momentum is actually a consequence of the isotropy of space. This statement we have also learned during the study of classical mechanics. Interested students can go through these concepts in classical mechanics again. That is, the conservation of angular momentum is actually a consequence of the isotropy of space. So, what is isotropy of space? This means that the physical laws governing an isolated system do not depend on the orientation of that system in space. So, in the present discussion, we will confined to the topic about orbital angular momentum, which is the counterpart of the angular momentum encountered in classical physics. So, in classical mechanics or classical physics, we tell about angular momentum, but in quantum mechanics, this terminology is orbital angular momentum. And angular momentum is a general concept in quantum mechanics, but apart from the concept of orbital angular momentum, there is an intrinsic property of elementary particles which is known as spin angular momentum, and it has no classical counterpart. For example, orbital angular momentum, the classical counterpart of the quantum mechanical orbital angular momentum is simply angular momentum. But the spin angular momentum, it is the intrinsic property of elementary particles, but it has no classical counterpart. And the total angular momentum of a particle is the vector sum of the orbital and spin angular momentum. And more discussion will be done regarding this statement in atomic physics. Now, we know that classically the angular momentum L of a particle with respect to some fixed origin O is defined as L is equal to R cross P. So, what is P here in equation 11.1? P is the momentum of the particle, and what is R? So, R is the position vector with respect to some origin O. So, this is the definition of the angular momentum in classical mechanics. So, L is equal to R cross P. Thus, L is a vector which points in a direction at right angles to the plane containing R and P. So, this must be true. So, as per the rules of the vector cross products, L vector should be at right angles to the plane containing R and P. Now, if we apply the rules of the cross product, then we can show that this L vector has three components. X component is Lx and is given by ypz minus zpy. Y component is Ly, which is given as zpx minus xpz, and z component of capital L is Lz, that is equal to xpy minus ypx. So, all this comes from the cross product R cross P given in equation 11.1. So, these are the three components of the L vectors. The corresponding quantum mechanical operator are obtained by replacing vector P and Px, Py, Pz by their respective operators. We have already read about the operator representation for the momentum. For example, Px, this is momentum operator. For Px, that will be minus I h cut del del x. So, for example, suppose Lx, you see at first this equation Lx equal to y pz minus zpy. So, how to represent Lx in operator notation? So, you see first term is y pz. So, we are writing y. For y, the operator is simply y, but for pz, that is minus I h cut del del z, because the operator representation for the pz is minus I h cut del del z. Now, you see that minus z into py. So, for z, that is simply z only, but for py, that will be minus I h cut del del y, but you have to check that there is a minus symbol here. So, you have to write this accordingly. So, this is for Lx, and in a similar manner we can also express Ly and Lz in operator representation. So, these are the operator representation for Lx, Ly and Lz. And similarly, we can also write the operator representation for capital L, this one. So, this is for 3 dimension. So, for 3 dimensional case, you have to represent vector P in 3 dimensional operator. So, that will be minus I h cut del. We know that what is del operator? Del operator means I del del x plus j del del y plus k into del del z. So, this is the del operator, as P is the vector and it is denoted in 3 dimension. That is why we are writing the operator representation of capital L in this way, that is minus I h cut r cross del. So, all these are the operator representation for the orbital angular momentum, and these are known as angular momentum operators. Now, we will discuss about some commutation relation regarding the angular momentum operators. So, we are going to obtain some commutation relation between Lx, Ly and Lz. For this purpose, we use the basic commutation relations between position and momentum operators. We have already read these in classical mechanics. Even in quantum mechanics we have already studied about this. For example, x comma px, y comma py and z comma pz, they all give I h cut. So commutation relation between x px, y py and z pz, they are same, and that is I h cut. And with all other pairs, for example x and py, they will commute with each other and they will become 0. For example, commutation relation between x comma py, that will be 0, x comma pz, that will be 0. Similarly, y comma px will be 0, y comma pz will be 0, etc. Now let us see that what is the commutation relation between Lx comma Ly. So Lx comma Ly, it can be written in this way, that is Lx Ly minus Ly Lx. Now what is Lx? We have already expressed those in these equations, that is, for example, Lx equal to y pz minus z py. So at first we have written the relation Lx Ly and Ly Lx by using these relations. Then after multiplication, it will give these terms, and some terms will be cancelled out. For example, if you look carefully, that is for example z into z, that is z square px py. Here is also z into z, z square py px. So these terms will cancel out. Some more terms will be cancelled out. So here there are 1 2 3 4 5 6 7 8, total 8 terms, but after some simplification only there will be 4 terms. So these are the terms, and they have again written in simplified format, that is we have taken common y px, and inside the first bracket we have written in this way, that is pz into z minus z into pz, then py into x, and here z pz minus pz into z. So so that this can be written in this way, z pz minus pzz into x py minus y px. So ultimately the term in the first bracket, that is commutation of z comma pz, and in the second bracket, that is x py minus y px. So that will give you actually ultimately, so z comma pz, that is Lz. So this can be written as Lz. Why? Because you see the relation here, that is Lz is equal to x py minus y px. So you see that is x py minus y px, that is we are writing as Lz, and z comma pz. What is z comma pz? You see here z comma pz is equal to I h cut. So ultimately this term will give you I h cut Lz, because I h cut comes from the this relation, that is for z comma pz, and for x py minus y px, that will give you Lz. So ultimately what we are showing here, you see that Lx comma Ly, that commutation relations between Lx comma Ly, that will give you I h cut Lz. And if you start in a similar manner, and we can also show that Ly comma Lz, that will give you I h cut Lx, and Lz comma Lx, that will give you I h cut Ly. Just you have to use the relations described here, this relation, and you have to simplify it properly, and so in that way we can show these 3 commutation relations. These are the commutation relations involving the angular momentum operators. So these relations are Lx comma Ly is equal to I h cut Lz, Ly comma Lz is equal to I h cut Lx, and Lz comma Lx is equal to I h cut Ly. So you have to memorize these commutation relations, because they are very important relations. Now what we see, that the operators representing any 2 components of the orbital angular momentum do not commute. You see Lx comma Ly. So these are the operators of the angular momentum for 2 different dimension. One is for x dimension and another is for y dimension. So operators representing any two component, that is x component and y component. Operators representing any two components of the orbital angular momentum do not commute. Why do not commute? Because you see in the right hand side it is not 0. That is why we are saying in this way, that is operators representing any two components of the orbital angular momentum do not commute. So what is the implication for this result? It implies that they cannot have simultaneous eigenfunctions and hence cannot be precisely measured simultaneously. This is very important consequence from the significance of the commutation relations or the operator algebra. We have already learned about the significance, that is what is the meaning of the commutation relations. So from those concepts we can say that if Lx comma Ly is not equal to 0, that is commutations for Lx comma Ly is not equal to 0, then it implies that that means these two components of the orbital angular momentum cannot be measured simultaneously and they cannot have simultaneous eigenfunctions. As such, it is in general impossible to assign definite values to all the components simultaneously. So from these three relations, what we can say that it is in general impossible to assign definite values to all the components simultaneously. Why? Because their commutations is not 0. In other words, if a system of particles is in an eigenstate of one of the components, it cannot be in an eigenstate of either of the other two components. So these are the significance of these commutation relations involving the angular momentum operators. Now let us now consider the square of the magnitude of the orbital angular momentum. So this is L square. So what is L square? L square is equal to Lx square plus Ly square plus Lz square. Now let us evaluate the commutation of Lx with L square. So this is L square comma Lx. So here for L square we are writing Lx square plus Ly square plus Lz square comma Lx. Now you see that L square comma Lx, that is left hand side, that can be written as in this way, that is you see here Lx square plus Ly square plus Lz square. So summation of three terms are there, but this can be represented as Lx square comma Lx plus Ly square comma Lx plus Lz square comma Lx. That is, this can be separated into three terms, but the first term, that is Lx square comma Lx is equal to 0. Why it is 0? Because we know from the concept or the rules of the operator algebra and the commutation relations, that is Lx square comma Lx, that can be written as Lx inside the third bracket Lx comma Lx plus in the third bracket Lx comma Lx multiplied by Lx. So commutation of Lx comma Lx is equal to 0. Commutation of for any two same variables, for example suppose a comma a, that is 0, we know that. So that is why Lx square comma Lx is 0. Now Ly square comma Lx, that can be written in this way by using the rules of the operator algebra and commutation relations. This can be expanded in this way, that is Ly into Ly comma Lx plus Ly comma Lx multiplied by Ly. Similarly, Lz square comma Lx, that can be written in this fashion. Now we know that is what is the value of Ly comma Lx or Lx comma Ly. All these we have already evaluated here. Just we have to put those values and we have to simplify those. So ultimately after simplification we can show that result of this summation will be 0. That means L square comma Lx, that will be 0. In a similar manner, we can also show that L square comma Ly and L square comma Lz, they are also giving 0 values. So what is the implication for these commutation relations? This shows that the magnitude of the orbital angular momentum, magnitude means L square, magnitude of the orbital angular momentum means L square, and any one of the Cartesian components can be simultaneously measured precisely, because as the commutation relation between L square comma Lx is 0, it means that L square and Lx, they can be measured simultaneously with precision. Therefore, it is possible to find simultaneous eigenfunctions of L square and any one of Lx, Ly or Lz. This statement is very important, because in the next lecture we will use this statement. Again I am repeating, that is, it is possible to find simultaneous eigenfunctions of L square and any one of Lx, Ly or Lz. Why? Because we are saying from the commutation relations described here. Now we will discuss something, that is angular momentum operators in spherical polar coordinates. In the previous sections we have shown that is how angular momentum can be described in Cartesian coordinates, but angular momentum operators, they can also be expressed in spherical polar coordinates. In order to obtain the eigenvalues and simultaneous eigenfunctions of L square and one of the component of L, we have already told that there is simultaneous eigenfunctions for L square and any one of the components of L. Simultaneous function means, suppose it is phi. So phi will be eigenfunction for both L square and any one of the component of L. This is the meaning of the simultaneous eigenfunctions. Now it is convenient to express the operators in spherical polar coordinates. It means that we will express the operators in terms of the r, theta and phi. Now you see that x, y, z, it is a three-dimensional Cartesian coordinate system, and any point, suppose the point is in P, so this point can be expressed for some coordinates x, y, z. So these coordinates are known as Cartesian coordinates, and this r is also known as position vector. Now the point P can also be expressed in polar coordinates. So if you express P in polar coordinates, then the relation between x, y, z and r, theta, phi can be expressed as x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. So these are the relation between the Cartesian coordinates and polar coordinates. So if we use these relations, then the operator representation of the angular momentum operators in polar coordinates will be like this. And we have to keep in mind, that is, the limit for r is from 0 to infinite, for theta it is 0 to pi, and for phi it is 0 to 2 pi. And we are omitting the detailed derivation, but after some derivations we are not showing here. You can check any standard mathematical textbook, that is how to transform from Cartesian coordinates to polar coordinates. So after that transformation, these operators, that is those what we have expressed earlier, that is for Lx, Ly and Lz, these operators, these are the operators in Cartesian coordinates. So these operators can be expressed in spherical polar coordinates after some mathematical steps that we are omitting right now. So after those steps we can show that Lx can be expressed in this way, Ly can be expressed in this way, and Lz can be expressed in this way. So these are the spherical polar coordinate representation for the orbital angular momentum operators. They are the three components for L. This is Lx, this is Ly, and this is Lz. So one important thing to note that for Lz, Lz depends only on the angle phi, but x component and y component, they depend on both theta and phi. And L square can be represented in this way. So 11.10 equation that represents L square. So these are the spherical polar coordinates representation for the L square. So I think you have already all understood what I have discussed so far. For more detailed understanding, I request to go through the textbook of MC Jain. So this is the end of the lecture.